Open up a 1920s crystal radio, and you'll find a tiny gray mineral called galena, the piece that pulled music out of thin air with no battery at all. For decades, that little stone has gotten the credit for launching the wireless age. But the component that actually rewired the modern world was a different crystal entirely, a sliver of quartz sitting on the other side of the signal, inside the transmitter. And that same sliver is now the timing heartbeat inside your phone, your laptop, and every GPS satellite overhead, anchoring an industry worth over $3 billion. But this story doesn't start with radio at all. It starts in a Paris laboratory in 1880, where two brothers, Pierre and Jacques Curie, were pressing on slices of crystal with little more than tinfoil, glue, and a jeweler's saw. What they found is called piezoelectricity. Squeeze a quartz crystal and it generates a faint electric charge. Feed it a charge and it flexes ever so slightly in return. It's a two-way street between pressure and electricity, and quartz happens to do it with remarkable consistency. For more than 30 years, though, it stayed a laboratory curiosity with no obvious job to do. The first time anyone put it to serious work, it wasn't for music or radio, it was for war. During the First World War, as German U-boats were hunting Allied shipping, the French physicist Paul Langevin sandwiched a thin quartz crystal between two steel plates and used it to fire a pulse of sound through the ocean, then timed the echo bouncing back off a submarine hull. That was active sonar, and at its heart was a piece of piezoelectric quartz doing the sensing. When the war ended, that same ability to steer vibration with electricity was about to find a far bigger home in the booming new business of radio broadcasting. Here's the detail almost everyone gets wrong. The galena crystal in those old cat's whisker radio sets and the quartz crystal that changed everything are two completely different inventions. If you've ever pried open an old cathedral radio or wired up a cat's whisker set, the crystal you were poking at was almost certainly galena, which is lead sulfide, and it worked purely as a detector. It rectified the incoming signal so you could hear it, but it had no power of its own and it never oscillated. The quartz line was a separate track altogether. In 1918, an engineer named Alexander Nicholson filed the first patent for a crystal-controlled oscillator using a material called Rochelle salt, though a priority dispute dragged the grant out until 1940. In 1921, the physicist Walter Cady built the first true quartz crystal oscillator. And in 1923, Harvard's George Washington Pierce patented the specific circuit that became the industry standard. Engineers still call it the Pierce oscillator today, and that same circuit is still in production almost exactly a century later. So why did quartz take over so quickly? The answer comes down to a problem that was slowly ruining early radio. The tuned circuits inside the 1920s transmitters drifted, wandering 3 to 4 kilohertz off their assigned frequency as the equipment heated up over a broadcast. Stations were packed just 10 kilohertz apart on the dial, so a transmitter that drifted would slide straight into its neighbor, and listeners at home got 2 programs bleeding into one garbled signal. By the mid-1920s, the airwaves were a crowded mess of overlapping stations, and regulators were desperate for anything that could pin transmitters down where they belonged. A slice of quartz, cut to vibrate at one exact frequency, locked a transmitter in place and held it there no matter how hot the tubes ran. In 1925, Westinghouse installed a crystal oscillator at its flagship station, KDKA in Pittsburgh. By 1926, quartz crystal control had spread across the broadcast band, and it had found an even hungrier audience among amateur radio operators. This part of the story rarely gets told. From the mid-1920s into the mid-1930s, It was not the big broadcasters who made up the largest market for quartz crystals. It was the hams, the amateur operators running transmitters out of their own homes and garages. In August 1925, the General Radio Company was selling finished crystals for $35 to $50 each, which was a serious amount of money in the 1920s, enough that a lot of operators chose to grind their own using instructions printed in QST magazine. Kitchen tables across the country turned into miniature crystal shops, with operators lapping slivers of quartz by hand until each one hit the exact frequency they were after. And out of that backyard scramble, a real industry was born, one whose descendants are still around. August Miller walked away from the optical lens business in 1923 to cut quartz blanks for hams. That same year, F. Dawson Bliley founded Bliley Electric, a company still operating today as Bliley Technologies. Herbert Blazier started Monitor Piezo Products in 1931, and Theodore Valpy founded Valpy Crystal the very same year. One town in particular, Carlisle, Pennsylvania, became a manufacturing hub that it remains to this day. It traces back to a Dickinson College physics professor named W.A. Parlin, along with his students and a local man named Grover Hunt, who stumbled onto the commercial potential of cutting quartz almost by accident after an abandoned side project turning petrified wood into a chess set. Up to this point, quartz was still just a radio part, a way to hold a signal steady. Then two Bell Labs engineers realized the same trick could keep time. In 1927, Warren Marrison and J.W. Horton built the first quartz crystal clock and showed it publicly at a conference that October. It ran a quartz resonator vibrating 50,000 times a second, then divided that fast, steady signal down electronically until it could drive an ordinary clock motor at a normal pace. When the New York Times covered the invention in 1929, the headline announced that an electrified quartz crystal had displaced the pendulum. It was the first timekeeper built around a vibrating crystal instead of a swinging weight, and it set the template for every precise clock that came after. The precision was unlike anything mechanical clockmakers could touch. Within a couple of years, refined versions were drifting by only about 1 second per 100 years under laboratory conditions, a figure so extreme it reads like a misprint. A fine mechanical pendulum clock could lose that much in a single day. For a while, the supply side of all this looked like a solved problem. Almost every crystal in an American radio was natural quartz, and nearly all of it came from a single country, Brazil, the only real source of electronic-grade natural quartz on Earth. That reliance on one distant supplier was a warning sign, and wartime planners had brushed past it for years. When the Second World War arrived, German U-boats began sinking the cargo ships carrying Brazilian quartz north to American factories, and suddenly, a mineral most people had never heard of became a genuine strategic crisis. Radios, radar, and field radios all depended on it. The U.S. War Department classified electronic-grade quartz as a strategic material and started subsidizing domestic mining in the Ouachita Mountains of Arkansas. In 1943 alone, the government bought 212,000 pounds of rock crystal, about 106 tons, for $35,000, and even that haul was not enough to meet demand. Brazil still supplied the majority of the war's quartz right to the end. Digging at home, in other words, never really closed the gap. The same shortage that nearly crippled American electronics is what finally freed quartz from the ground for good. After the war, Bell Laboratories worked out how to grow quartz crystals artificially inside high-pressure vessels that mimic the heat and pressure found deep underground. And by 1950, the process was commercially viable. This was the moment quartz stopped being a wartime bottleneck and started becoming something the world would eventually manufacture by the billions. Within 2 decades, the changeover was almost total. By 1971, natural quartz had lost its lead for good, and nearly every crystal in electronics was being grown in a factory rather than pulled from a mountain. Within a few years, a material that had once triggered a national emergency could be produced on demand in a lab, in whatever quantity the electronics boom called for. Which brings us to the device in your pocket. This next detail is the one that ties the whole story together. Nearly every gadget with a clock function, your phone, your laptop, your camera, even the smart meter on your house, keeps time using a quartz crystal cut to vibrate 32,768 times a second. That oddly specific number has a clean reason behind it. It's 2 to the 15th power, which means a simple 15-stage binary divider chops that fast vibration down into exactly 1 clean tick per second. GPS leans on quartz even harder. A satellite receiver carries its own temperature-compensated quartz oscillator as a local reference clock, and it works out your position by measuring the timing of incoming satellite signals against that steady local tick. If the crystal's frequency wanders even slightly, your location fix gets slower to lock and less accurate once it does. Whole systems ride on that steadiness, from cell towers keeping their networks in sync to the navigation in your car finding the right street. And the little circuit doing the oscillating inside a modern real-time clock chip is a direct descendant of the one Pierce patented back in 1923. Think about that for a second, because a 100-year-old radio circuit is running inside the phone you're holding right now. All of that adds up to real money. Ask a handful of research firms how big the crystal oscillator market is, and you'll get a handful of different numbers, all of them hovering around $3 billion in 2025. They agree on the ballpark and argue about the edges, because a market this fragmented is only ever as big as the definition you use to measure it. The growth is being driven by 5G networks, automotive electronics, and in the newest reports, the enormous timing demands of AI data centers, which need ultra-stable clocks at massive scale. Now, you might assume the companies cashing in are mostly Chinese, but that guess turns out to be wrong. The market is actually dominated by Japanese firms, Seiko Epson, Murata, Kyocera, and Nihon Denpa Kogyo, which together with America's microchip technology hold close to half of it. Taiwan, New Zealand, and a cluster of American makers fill out the rest of the field. But there's a twist worth ending on. Quartz is now facing a real challenger for the first time. A California company called SiTime is building oscillators out of silicon instead of quartz, and it claims its silicon chips run about 10 times steadier than quartz inside AI servers, while taking up roughly half the physical space. So for the first time in a century, the little crystal that quietly ran the 20th century has a serious rival. Today it still keeps perfect time in the phone in your pocket, but in the newest data centers, a sliver of silicon is already starting to take its place.